So finally, we want to look at a couple of cases for medical image computing, right? So this is also the computation efficiency is also very important, right? Because in a lot of hospitals, right, they do not have powerful GPUs, right? They may only have computers only have CPUs, right? But if you have a deployed deep learning network that requires high capacity hardwares, if you want them to change the entire infrastructure, is quite challenging, right? Because it's have to spend a lot of cost to change the entire infrastructure, right? It's better to do something on the software level rather do something on the hardware level, right? So we need to develop some efficient network, maybe can even run using CPU efficiently, right? So that's the goal, right? For developing the efficient network for medical image application. So in this work, right, they do this efficient medical image segmentation based on knowledge distillation. Okay, so the idea, just using a large teacher network, right? You have a smaller student network, and you are using this kind of different levels of supervision, right? The feature map level, and you also have basically the logics, right? The logic is the segmentation, right? You have this predict segmentation map as the supervision to do the knowledge distillation. And in this case, they are able to generate a much smaller student network, right, with much smaller number of parameters, but have similar, segmentation accuracy in terms of the DICE score. Okay. And the next work is our work at the ECCV 2022. This is a dynamic network. So again, just like the MutualNet, right? We consider this dynamic network that is able to change the structure based on the input. Okay. So the observation we have is, if we look at the volumetric segmentation, right, this brain tumor segmentation, these are the MRI scans of different slices, right? And you can see that because these are the cross section, right? The slices are one cross section of the brain, right? When the scan, MRI scanner or the CT scan, right? So they cut different cross sections, right? Some of the scans or slides does not even contain useful information for tumor segmentation or detection, right? So for this slices, I also overlay the segmentation map for the tumor, right? For some of the slices, they don't have much information. Even the normal tissue don't have much information there. Some of them, the initial slides are just pure black, right? In this case, we can consider them as an easy slice, right? We don't need to have a fixed segmentation network run through all these slices, every slice, right? Only for some of the difficult slice, right? Maybe this one contain multiple tumor type, right? We need to run a complicated network in order to segment these different type of tumors, right? Maybe for this one only contain one or two type of tumors, we can using a much simpler network able to do the segmentation accurately. So that's the intuition, right? Can we, adjust the network complexity to cope with the different input? Okay. So again, we consider we have an option of totally skip, right? So basically for this one, we can just predict there's nothing there. There's no, tumor, right? We output a segmentation map of 0, okay? So that we don't incur any of the computation, okay? But for some of the easy case, right, we have a light model to do the segmentation to generate the corresponding segmentation network. But for some of the complex slides, we're using maybe the most complex model to do the prediction. So that's the idea. To achieve this, we specify a couple of candidate network. So in this kind of model bank, we say, basically we have n candidate network. So can be efficient network like a MobileNet, ShuffleNet, or simplified UNet, right? And then we can have more complicated network, can be vision transformers to do the segmentation, right? These complex network has larger network parameters and large compute. Okay. And we just learn a decision network or policy network, right? Which candidate we want to use based on the current input, right? We also have an option of totally skip, right? We don't do any operation. We just predict output with, just 0, basically. Okay. So we train this network and with the objective of reducing the total computation. At the same time, we have the segmentation accuracy, right? So we have two loss objectives. One is the performance. The other is the total number of the computational cost for the network. Okay. And once we train this network and we do some evaluation, right? So in terms of this usual segmentation performance, in terms of the dice score and the Hausdorff distance, we also do, we count this flops, right? And if we compare with some of the large network, like this 3D unit VNet, right? These are the 3D networks, right? You can see how many floating point operation these large network have, right? We are able to reduce the computation significantly, but at the same time, right, we are able to achieve even the best score, right, for some of the tumor type, right? This enhanced tumor, right? We are able to achieve the best accuracy. This enhanced tumor actually is very important, right? It's an important category. So we are able to achieve the best accuracy for this particular tumor type. Okay. Okay, so here finally I list some of the reference, for basically the survey papers in terms of knowledge distillation, quantization, pruning. So if you're interested, you can check out these, survey papers. They will be very good reference for you to identify some of the algorithm that you want to use. Okay.